Okay, welcome. Yeah, I said okay that time. That's good, huh? Welcome to a beautiful day. The clouds are breaking, the sun is shining, and we are all here to do some 1.3 with some surprises. We're talking about the fundamental theorem of calculus, and we're also going to start by talking about the mean value theorem. Now, both of these theorems have rather long names, so we will be abbreviating them. You will probably never see me write fundamental theorem of calculus or mean value theorem in a video ever again. I will always be writing FTC and MVT, and we will still say fundamental theorem of calculus or mean value theorem. Sometimes I say the abbreviations too, but that's okay. All right. And kind of the overview of what we're doing in this section is shortcuts. So, we started by introducing areas under curves and showed that, wow, these are actually the same as the net change. If the area is under the derivative, that's the area under the curve is the net change of the function. Whoa, that's crazy. And then we started talking about, all right, Riemann sums, summation notation. How do we actually find the area under the curve? And then we showed, oh, the area under the curve is a definite integral. We can calculate definite integrals using sums. And it was all very tedious and interesting and how it all connects together, the nuts and bolts. Well, now that we got the nuts and bolts out of the way, let's slap some shiny plastic on this thing so we can make it more user-friendly. I think that metaphor might work. Anyway, so that's the introduction. That's where we're at today. And we're going to start by talking about the mean value theorem for integrals. But not in green. I do like green, though. The mean value theorem for integrals. Let's capitalize the I. Be very official here. The mean value of theorem for integrals, I'll write out the theorem, and I think it'll make a lot more sense once we really see what the theorem means. But let's say that we have a function f, and that function is continuous over the interval from a to b. Then there is, hold on, I should use a comma here. Good grammar. Then there is at least one c, and this should sound a little familiar. At least one. All right, this is the problem when I say different things than when I write. There's at least one. Oh wait, I can't make some look like one that easily. There is at least one c in the interval. We're going to use some shortcut notation. This is like an element sign. It kind of looks like a C with a middle bar, like a hybrid of a C and an E. There's a C in the interval from A to B with the function value at that C. So the height of the function at that input value C, and there's at least one of those C's, is equal to 1 over B minus A times the integral from A to B of the function with respect to X. And now this doesn't look super easy, but notice what this is. Got a little hint for you. We talked about it last section. This is just the average value of f from B to A, from A to B. I cannot write anything today. This is going to be an interesting set of videos. Okay, so all this is saying is that if we have a continuous function, we're looking at that continuous function on some interval, there's a point where the average value of the function is achieved. In other words, it's impossible for the average value to be skipped. The function must hit that average value somewhere. To give some little pictures, and this should remind you of the intermediate value theorem. All right, let's just say this is our interval from A to B, and maybe our function, maybe our function looks like this. Well, then we know there's an average value. This is a continuous function. We know there's an average value, and let's say the average value of this function is, I don't know, maybe here. All the theorem says is that there's at least one input around here such that this value is hit. And so it guarantees the existence of this C. It guarantees the existence that there's at least one of those C's. And maybe there's going to be multiple, right? Maybe we have a function that, does all sorts of things. It's going all around, again, from A to B. It doesn't have to be positive. Maybe the average value is right here. Well, this guarantees that this average value is attained. And in fact, in this case, it's a hit here, 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 and here. So there's a lot of C's in this second case. Another way of thinking about this mean value theorem is that if we draw a little rectangle, the area under the curve is the same as the area of this rectangle. Area under the curve, let's pretend these are all in a straight line. The area under the curve is the same as the area under that rectangle. Another way of thinking about and connecting the mean value theorem with what we know about average values. All right, so that's all the mean value theorem says. We'll talk about how we use it soon. I don't want to spoil it, but just be on the lookout for the mean value theorem, all right? Average value is achieved for continuous functions. But in the meantime, let's do 2 examples. And then, believe it or not, after 2 examples, we're just going to be done this video. It's not even going to be 30 minutes long. Whoa! Did you know that was even possible in this class? Well, now you do. Well, I'm speaking soon. I don't think this video will be 35 minutes long, but who knows? Maybe these examples are just going to go on and forever. So find the average value, f bar, also known as f average, over the interval from 0 to 4, where the function f of x is equal to 8 minus 2x. And, so I want you to do 2 things here, and find the c. That's not how you write a c. Find a c with f of c equaling that average value. So we're going to find the average value, and then we know by the mean value theorem for integrals that if we have a continuous function, there's at least one place where that average value is achieved with the function. All right, so let's do it. Remember your formula for average value. It's going to be 1 divided by b minus a, so just dividing by the width of that interval. The integral, or the area under the curve from a to b, of that function with respect to x. And so in our case, that's going to be 1 over 4, integral from 0 to 4, of the function, which is 8 minus 2x. With respect to x, later on in this video, we're going to have a shortcut for how to do this. But in the meantime, we're going to do it graphically. Okay. We're going from 0 to 4. Let's say 0, 1, 2, 3, 4. Looks something like that. 8 minus 2x has a... 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8 minus 2x starts up here, has a slope of -2. Oh wait, I have graph paper on this. I have graph paper on this tablet. I was wondering why it felt so hard, because I wasn't using my graph paper. So the average value is just the area, right? And from 0 to 4, that's just a triangle. 1/2 base times height. So this integral is the area, which is 1/2, the base, which is 4, times the height, which is 8. And we could simplify all of this to get 1/8 times 8 is 1, times 4 is 4, which makes sense that the average value would be 4 here. Right? It's a straight line. So if it's a straight line and it starts at 8 and ends at 0, average value equaling 4 should make sense. So again, that tells us that this is our average value right here. And hey, this was guaranteed by the MVT. And here's the location. The location is at 2. We know f of 2 equals 4. So that c value that we're looking for, and there might be multiple. In this case, our c value is just 2. That's it. That's this whole video. All right. Isn't that nice? Like I said, a little sunshine coming down. All right. Let's do one more example just for some extra practice. Example 2. Suppose the definite integral from 0 to 3 of the function x squared with respect to x, that definite integral is equal to 9. Find c with f of c equaling f average over the interval from 0 to 3. Now, in order for this c to be guaranteed, in order for you to know I'm not sending you on a wild goose chase, we need that our function's continuous. But look at our function. Our integrand, the inside of the integral without the dx, the function on the inside of the integral, our integrand is x squared. Yeah, that's a continuous function. That's a polynomial. All polynomials are continuous. All right. So we know we're continuous over 0 to 3 because we're continuous for all real numbers. We know this c exists. We know I'm not sending you on a wild goose chase, which does happen from time to time on accident. Well, you'll know whether it's on accident or not. If it's not on accident, if I ever do it on purpose, I'll laugh and say something like, I tricked you. Otherwise, I'll say I tricked me. Okay, so we know this, right? First off, we need to find a c that has this true, so we need to find what the average value is. So the average value, again, f bar, f av, they mean the same thing. That's just 1 over b minus a times the integral from a to b of our function with respect to x. We already know that this is 9. I know that that's 1/3. I definitely wrote 3 at first, but it's 1/3. So it's just 1/3 times 9. Should be the average value is 3. And if we graphed it, we're not done with the problem, but I just want to, be on the same page. If we graphed it, we looked at, okay, let's look at this function from 0 to 3. So let's maybe, all right, I'm saying that the average value is 3. Does this look about right? One of the ways to think about average values is that this area should be the same as this area. The area between this horizontal line and the function should be equal for the aboves and the belows. And I mean, I'm not going to count all these squares, but that's one way that we could do it. We could do an estimation by counting these little squares. That would be another way of doing a Riemann sum, is counting these squares in Desmos and then just making like approximations, saying like, oh, maybe that's 1/4 of a square or something like that. But yeah, it looks plausible. If I told you the average value was, 7 or something, you'd be like, no way that's 7, Jason. Come on, this area down here is way bigger than that. That's just kind of when you have technology or when you can graph things, it's kind of a good way to kind of get a gut feeling. It doesn't prove anything, but sometimes it can show you that, oh no, that doesn't look right at all. This doesn't look right at all. This, maybe it's right, maybe it's not, but it looks believable. So that's the average value, but it's not what we're asked to find. We're asked to find a c where the function hits the average value. And of course, when I graph it, you can find the c very quickly. But how would you do it if you didn't have the graph? Well, we need f of c equal to 3. Well, what is f of c? It's when we evaluate our function at c. So that's when c squared is equal to 3. When is c squared equal to 3? I don't know, but I can find out. Square root both sides. That's when c is plus or minus. Do not forget the plus or minus. The square root of 3. So it happens 2 places. We only want one of them. So our c value should be the square root of 3. For applications, I like approximations. For theoretical questions like this, I would like your exact answer, which is the square root of 3. It's about 1.7, I think. Let's see if this is consistent with Desmos. That looks pretty good. What is the square root of 3? Nice. Yeah, so it is indeed square root of 3. We did it. And that's the whole video. Hey, not 35 minutes. How about that? Let me know if you have any questions. Get started with the problems and have a great one.